So in this video, we're going to talk about the relationship between continuity and differentiability. Right? We've talked about continuity. What differentiability means is that you can take the derivative. So basically that the derivative exists. Okay, so we can read through this if we want to. That'll kind of go into that a little bit more. Now, before we discuss these three functions, what I want to do is just kind of talk about that differentiability very quickly. So when functions are not differentiable, we have a few cases for when they're not differentiable. So I want us to just draw these out. So we're going to basically draw four graphs right here. And so our first graph is going to be the graph, and if you want to use another color, you can, I'm going to. The graph of any corner. Right, so at the corner, we're not differentiable. And the reason for that is the slope exists on the left side, right? Like we can take a derivative over here. We can take a derivative over here. But it doesn't exist at the corner. And the reason for that is like kind of the left, if we went really, really close, the tangent line there has a negative slope. And really, really close on the right side, the tangent there has a positive slope. Those tangents are not approaching the same value. Right? If we thought like, can we just draw one tangent here? No, we can draw like a bunch of different tangent lines here that touch that graph once, right? And a tangent line is a graph that touches it once. So since there are so many different options at that point, we say it's not differentiable at that corner. So at any corner, our graph will not be differentiable. Okay, our next case is going to be a cusp. And what a cusp looks like is it's a corner that kind of is curved, right? We always want to have arrows on these, by the way. So at that point, kind of the same exact thing happens where we're not going to be differentiable at the cusp. Okay, and some textbooks will kind of combine corners and cusps. They're very similar. Okay, our third case is going to be a vertical tangent line. So anything that, not a vertical asymptote, but a vertical tangent line. So when the slope of this graph here at this point is vertical, like if that tangent line was vertical tangent line. So at that slope, we say the derivative doesn't exist. And the reason for that, like the slope of a vertical line is undefined. So since the slope is undefined, we say it's not differentiable. And the fourth case is a little bit of kind of a cheat, is anything that's not continuous. So we had quite a few cases of these. We had, kind of a jump, right? We had our cases where jumps, right? Holes. We had vertical asymptotes. And the fourth one is kind of that weird one, that oscillation. And we'll review that fourth one later. But anything that's not continuous, right, as well. We can't take the derivative when it's not continuous. So those are our four cases. Now, in terms of the analytical, that's the graphical side. In terms of the analytical side, kind of what you're looking for, piecewise functions especially. Piecewise functions are big. But also absolute value. Like if I have the absolute value of x, that's going to create a corner. For cusps, we can also have the absolute value with like an x squared. That might create a cusp. Or also x to any even, like 2/3, where we have an even numerator fraction and then an odd denominator fraction. That'll create a cusp. And vertical tangent lines are odd over odd. So if we have like 1/3, that'll create a vertical tangent. So anyways, let's jump into these and just kind of explore them. So if we're going to consider the function f of x equals square root of x squared minus 4. So on the graph, x squared minus 4, we're going to, this is actually kind of a half circle. And so what this is at positive 2 and negative 2, this creates a half circle. Okay. And actually, I'm sorry, I totally did the absolute wrong thing on this. You can graph this on Desmos. This is actually kind of a weird one. This is the opposite of the half circle. This is the square root, looks like this, but because of the x squared, we also get it on the left side. So we get at positive 2 and at negative 2. So this is kind of weird function. So you could use Desmos to get that. Now, based on the graph, is it continuous at 2? It's not, but we need to kind of show with the 3 rules. So the first rule, f of 2 does exist. F of 2 is equal to 0. That exists. But for the second rule, right, the limit as x approaches 2 on the right side exists. On the right side, we are approaching 0. But on the left side, there is no left side at 2. Right, so on the left side, that doesn't exist. So because those two are not equal, what this kind of tells us is that the limit, the overall limit as x approaches 2 of f of x, does not exist. So therefore, f of x is not continuous at x equals 2. Now that gives us the what, it's not continuous, the where at x equals 2, and the why was because the limit didn't exist. The therefore kind of takes care of it. It also used because. Find the value of f prime of 2. So if we're going to find f prime of 2, first we have to find f prime of x. This is going to be chain rule. 1 over 2 square root of our box times the derivative of our box. The 2's cancel, and that gives us x divided by the square root of x squared minus 4. Now we can plug in 2, so f prime of 2, that's going to give us 2 divided by the square root of 2 squared minus 4, which is 2 over square root of 0, which is 2 over 0, and that's undefined. So we can say f, basically they asked, is it differentiable at 2? Determine if it's differentiable at 2. So f of x is not differentiable, that's the what, at x equals 2, that's the where, because f prime of 2 does not exist, that's the why. So what, where, and why, that's always the three things that we need. Okay. Next one we have, we're going to do another graph. This is x to the 1/3 plus 2. Again, you can just use Desmos to graph this. But what this graph is going to look like is at 2, it's going to have a little bit of a vertical tangent. And it's going to kind of look almost like a square root and then an upside down square root. Okay, and actually that doesn't even go that far down. If you look at Desmos, it more kind of tails off this way. So based on the graph, is this one continuous at x equals 0? And at x equals 0, that's kind of right here at that 2, it is continuous. So we're going to say our first rule, we have to prove it with the 3 rules. F of 0 equals 2, that exists. Our second rule, we need to do the limit. And in order to prove the limit exists, we need to show that the left limit is equal to 2, and the right limit is equal to 2. So since they're both 2, we can say that the overall limit, this is important, we need to write the overall limit also equals 2. Okay, and then our third rule, f of 0, not f of 2, it's 0, they both equal to 2, equals the limit as x approaches 0 of f of x. They were both 2. Therefore, f of x is continuous at x equals 0. Okay. Find the value of f prime of 0. So now before we can find f prime of 0, we always have to find f prime of x. So 1/3 x to the negative 2/3 power, that would be the derivative. The plus 2 part goes to 0. Now I'm going to rewrite this whenever I plug in. I always like to rewrite it in radical form. So I'm going to move it to the denominator to take away the negative exponent. And then this is going to become the cube root of x squared. Right, that's our radical form. The numerator, the 2, stays with the x, and the denominator becomes the root. So now f prime of 0, that's going to become 1 over 3 times the cube root of 0 squared. Well, 0 squared is 0, cube root is 0, 0, 3 times 0 is 0. So we get undefined again. So this is going to be the same reasoning as the last time. F of x is not differentiable at x equals 0 because f prime of 0 does not exist. So nice and simple. Okay, and then our last one is going to be x to the 2/3 power. So same process, we're going to do the exact same process again. So when you graph this one on Desmos, you're going to get same, y-intercept is 2. That should be obvious from just looking at it. But then this one looks like a square root graph, but kind of on both sides flipped. And so that's what x to the 2/3 graphs look like. And so based on this graph, is it continuous? Well, looking at it, yes, but we can't just say it's continuous because it's connected. You always need to justify with our 3 continuity rules. So f of 0 equals 2, that exists. This is essentially the almost exact same repeat as the last question. Then to prove the limit exists, we need to show the limit of the left side and the right side. So the limit of the left side is equal to 2. The limit of the right side of f of x is equal to 2. So the overall limit as x approaches 0 of f of x equals 2. Okay, so then our third rule, f of 0 is equal to the overall limit. And we always need to write in that overall limit. That's important. Some of you guys have been forgetting that. So it's important to both write the left, the right, and then show the overall. So therefore, f of x is continuous. That's our what? At x equals 0. That's the where. And the y kind of is from the therefore and all the work. Find f prime of 0. So same steps. First, we're going to do f prime of x. We're going to bring the 2/3 down. Then x to the negative 1/3. That's a perfect answer, but since I know I'm plugging in, I like to get this back into radical form. So bring the x to the 1/3 to the bottom to make the exponent turn back positive. And change this into radical form. It's going to be the cube root of x to the first, or just the cube root of x is fine. You don't need that to the first power. Then f prime of 0, 2 over the cube root, 3 times the cube root of 0. Cube root of 0 is 0, times 3 is still 0. So 2 over 0, which is undefined. We don't need to write 2 over 0. So that's undefined. And same reasoning we had before. So f of x is not differentiable. Notice that I'm not saying f prime of x. Right? I'm saying f of x is not differentiable. At, so that was the what? X equals 0, because f prime of 0 does not exist. So f prime of 0 does not exist. So that's our what, our where, and our why. So based on this, we're going to kind of talk about this, does continuity imply differentiability and vice versa. But before I do that, I want to just kind of review. So this was our cusp, right? And in the beginning, we kind of talked about that even exponent over an odd exponent, the fraction. And it was continuous. So kind of yes, it was continuous, but no, it was not differentiable. Then coming back up here, we had our vertical tangent. And on our vertical tangent, right, we said it was when we have an odd over an odd for our fraction. And yes, it was continuous, but no, it was not differentiable. And then going back up to the first one, we had this one was our not continuous case, which we get a lot, especially in piecewise or with square roots when they're negative, they're going to be DNE, or with fractions, like the denominator is going to be DNE, but not continuous. So this was no, it was not continuous, and no, it was also not differentiable. So we can kind of basically take this and write, first of all, continuity does not imply differentiability. And what this means, we saw this in cases 2 and 3, is that when a graph was continuous, that does not mean that it's going to also be differentiable, right? So kind of what we can say is, easier, if f of x is continuous, essentially what that means is we just don't know. We don't know if it is differentiable. We have no idea. Okay? But then if we kind of flip this, differentiability, if a graph is differentiable, does imply continuity. And so what that tells us is that if a graph is differentiable, then it first had to have been continuous. So if f of x is differentiable, then we know f of x is continuous. And so what that tells us is anytime we know it's differentiable, it also has to be continuous at that spot. So in order for it to be differentiable, we're going to have two rules, right? Continuity, we had three rules. We reviewed them above. F of x exists, the limit exists, and those two are equal. Differentiability has two rules. And the first rule is kind of what we just said, is that in order for it to be differentiable, it had to have first been continuous. So our first rule is f of x must be continuous. And we'll kind of say at x equals a, right? Like at some point, because sometimes we're just doing these at a point. So at x equals a. And the second rule is a little bit trickier. It's that the limit as x approaches a from the left side of f prime of x, not of f of x, but of f prime of x, must equal the limit as x approaches a from the right side of f prime of x. And so what this is saying is that basically the derivatives are approaching the same value. And that really comes into effect with, if we look up here at our cusp, right? If we look at this one was not differentiable, well, first rule was, is it continuous? And if we look at the graph, yes, it's continuous. But if we look at what was the derivative approaching, if I kind of took the derivative really close to this point, right, the limit of the derivative is approaching kind of a negative value. So this would be the limit as x approaches 0 on the left side of f prime of x. That's what that's going to look like, is that negative slope. And I'll use another color, right? On the right side, if we went really close, we're getting, that's our tangent line. That tangent line would represent the limit as x approaches 0 from the right side of f prime of x, right? F prime being the slope of the tangent. And those tangents are not, their slopes are not approaching the same number, right? The blue one's a negative number, the red one's a positive slope, right? We're just looking at the slopes. They're not going to be the same. And so that's showing that those are not equal. And that's just kind of what that language means. Now, can we do what we just did and take the derivative and plug it in and get undefined? Absolutely, that works. But for piecewise functions, which these are going to be really popular with piecewise functions, we are going to have to take the left derivative and the right derivative. So we'll kind of show what this looks like. So consider the function g of x equals the square root of x plus 1 for 0 less than or equal to x less than or equal to 3 and 5 minus x. Now, to show that it's differentiable, our first step always must be to show it's continuous. Sometimes what happens with these is, and I've seen this a lot, is the second rule actually passes, and students will just say, oh, it's differentiable because the second rule passed, but the first rule failed. And so this would mean if one failed and one passes, this would mean it's not differentiable. But what a lot of students do is they kind of try to cheat and they skip the first rule and they jump straight to the second rule. So we always need to first look at the continuous part. Now, if there's multiple choice, all you have to do is, we're looking at x equals 3. All you have to do is plug in 3 to both of these and see if you get the same answer. But if it's free response and they're saying show your work, then we got to do the 3 rules. So first rule, f of 3 exists. Now, when we just isolate 3, less than or equal to, this would be the left side from the less than and the equal side for that equal to part. And 3 greater than x, if we kind of flip that, that's x is greater than 3. That's our right side, right? 3 is less than x is the same as x greater than 3. So f of 3, that was our left side. So this is going to be the square root of 3 plus 1. That's the square root of 4, which is 2. Second rule, the limit as x approaches 3 from the left side, we just said that that's the top. We're going to write of f of x is equal to, again, the square root of 3 plus 1, which we said was 2. And the limit as x approaches 3 from the right side of f of x, that's going to be the bottom one. 5 minus 3, that's also 2. So then we can say that the overall limit as x approaches 3 of f of x equals 2. If you want to add in, because the left limit equals the right limit, that's great, but, it's kind of obvious we showed our work. Then our third rule is f of 3 is equal to the limit. And in this case, we can write that they are equal to because we got 2 for both answers. So therefore, f of x is continuous. That's the what. At x equals 2, that's the where. And the y is from the therefore in the work. Okay, second part says, is f of x differentiable? And show our work. So the way we're going to do this, g of x, I've been saying f the whole time. These all should have been g's. So g of x, g of 3, limit as x approaches 2, g of 3, g of x, g of x, g of x, g of 3. Okay, there we go. So is g of x differentiable at x equals 3? So the first step is going to be to take the derivative. Now, we haven't taken the derivative piecewise yet, but it's actually very easy. You literally write everything the same, except basically the function parts, the square root of x plus 1 and the 5 minus x, you take the derivative of those. But everything else ends up being the same. So this top one is chain rule, square root of 1 over 2 square root of, that's kind of like our box, x plus 1 times the derivative of x plus 1 is 1. So we can drop the times 1 if you want to. And then that's for 0 less than or equal to x, less than or equal to 3. We write that part the same. The derivative of 5 minus x, the 5 part goes away. The derivative of negative x is negative 1. And that's for 3 is less than x, which is less than or equal to 5. So again, this was our left side and our equal side. And this is our right side. You don't need to write that left, this part in, but if you want to, it helps me to kind of write it. So now, what we're going to do is when we do the limit as x approaches 3 from the left side of g prime of x, we're literally just plugging in to the 3 into the left side. So we're plugging in 3, wrong 2. There we go. We're plugging in 3 to this left side. So that's going to be 1 over 2 square root of 3 plus 1. That's 1 over 2 square root of 4. Square root of 4 is 2. 2 times 2 is 4, so we get 1/4. And then the limit as x approaches 3 from the right side of g prime of x. And this one's going to just be negative 1, right? That's our right side, was just negative 1. So now, these two are not equal. So we're going to say f prime of x does not exist, right? And that's because of those two. And so we can kind of say f of x is not differentiable because f prime, and we're using g, I don't know why I keep going back to f. So g prime of x does not exist, and so we're going to say g of x is not differentiable. Oh, I need my where, right? That was the what, we need our where. At x equals 3, and then the y is because the limit as x approaches 3 from the left side of g prime of x does not equal the limit as x approaches 3 from the right side of g prime of x. So my what, my where, and my y. Okay. Next question. These are a little bit tricky, but they're very, very common on the AP exam. And so sometimes they'll say both continuous and differentiable, and sometimes they'll only say differentiable. We'll talk about that in the next question. But we're always going to do these the same way. So in order to make k and m continuous, and I always kind of split this up, in order to make them continuous at x equals 3, what would have to be true is these two sides would have to be equal, right? If those are equal, then we're going to get continuous. So we're going to say k square root of x plus 1 would have to equal mx plus 2, but what is it? It's at 3, so we're going to plug in 3. So k square root of 3 plus 1 would have to be equal to m times 3 plus 2. We'll clean this up. Square root of 3 plus 1 is square root of 4. Square root of 4 is 2. So 2k would have to equal 3m plus 2. This is kind of our first equation. Then in addition to that, we're going to have to do a differentiable case. So they're going to have to be differentiable at x equals 3. And before we can do differentiable, we always want to take the derivative. So we're going to do h prime of x and h prime of x. Now, k is just a constant. It's literally going to just hang out. So k times 1 over the 2 square root of x plus 1. Technically, that's a box, right? Like chain rule times 1. You don't really need the times 1, but I'm going to write it. That was for 0 less than or equal to x less than or equal to 3. Then in the bottom case, m is just a constant. What's the derivative of 3x? 3. The derivative of mx is just m. When 3 is less than x, which is less than or equal to 5. So now, for the differentiable case, we want those two sides to be equal. So you can rewrite it, with the k on top if you want to, but I'm going to just write k times 1 over 2 square root of x plus 1 has to equal to m. And again, it's at 3, so we're going to plug in 3. K times 1 over 2 square root of 3 plus 1 would have to equal to m. That's square root of 4. Square root of 4 is 2. 2 times 2 is 4. So k times 1/4 equals m, or 1/4 k must be equal to m. So this is our second equation. Now we have two equations and we have two unknowns. So what we can do is we can solve one and then substitute. We already have m solved. So what we can do is we can kind of take that 1/4 k and plug that in where we see k. This is going to be 2 times 1/4 m is equal to 3m plus 2. If you didn't want to have fractions, by the way, you could have multiplied both sides by 4 on this one and gotten like k equals 2m. That would have worked too. So this is 1/2 m equals 3m plus 2. And you can subtract and get like 2.5, or basically it's 5/2. Or if you're like me and you don't like fractions, you can just multiply every single term by 2 times 2 times 2 times 2. And so that'll give us m equals 6m plus 4. Let's kind of write our work over here. So this gives us, if we subtract m, we get 0 equals 5m plus 4. Subtract 4, divide by 5, we get negative 4/5 is equal to I think I might have messed that up somewhere. Let me just check my work. I think I made a small mistake. Yeah, actually I made a little bit of a bigger mistake. So I plugged in this. This is what is equal to m. So we weren't supposed to plug it in for k. We were supposed to plug it in for m, right? Because it's m is equal to 1/4 k. So all of that work I totally did wrong. So sorry about that. We were plugging in for m. So what should have happened is we should have had 2k equals 2k equals 3 times, now for m is equal to 1/4 k plus 2. There we go. So this would be 2k equals 3/4 k plus 2. And I'll do the same thing I did before, which is multiply every term by my denominator. In this case, my denominator is 4 times 4 times 4. There's a plus sign here, so we're going to multiply the 2 by 4. It gives us 8k equals 3k plus 8. Let's write our work up here. So we can subtract both sides by 3k. That gives us 5k equals 8. And so we get k equals to 8/5. And that is the right answer. I don't know what I was doing before. Now that I have that, now we can plug back into this equation that was solved. So 1/4 times, now we're plugging in for k because now we have k. 1/4 times 8/5 equals m. 4 and 8 cancel to a 2. So we get 2/5 is equal to m. So this process is the same for every single one of these questions. What can be different is they might just say differentiable. So they might just say, for what values of a and b will we have differentiable? And what a lot of students do is they just jump straight to the differentiable case. Right up here, see we have like the continuous side and the differentiable side. They just jump straight to differentiable because that's all they see. What you need to remember is this problem is very common and it's always the same. And remember, we said differentiability implies continuity. So for what values will it be differentiable? Well, if it was differentiable, it also had to be continuous. So we're still going to actually do those two cases. We're going to do, when is it going to be continuous? at x equals 1? And when is it going to be differentiable at x equals 1? So we're going to do both cases. So first, we're going to do the continuous case. We're going to just set 3ax squared. And if you want to, you can just start plugging in the x. So 3ax squared plus 2bx plus 1 equals ax to the fourth minus 4bx squared minus 3x. This gives us 3a plus 2b plus 1 is equal to a to the fourth minus 4b minus 3. Not a to the fourth, a. 1 to the fourth was 1. A minus 4b minus 3. There we go. So that's our first equation. Our second equation, I'll use red, we're going to do for differentiability. So before we can set them equal to, we have to first find the derivative. So we're going to do f prime of x is equal to, and now always take the derivative before you plug in. So you're always going to take the derivative up here before we plug in. The derivative 3ax squared. 3a is just a constant. So when we multiply 3a times 2, we get 6a and x to the first power, just x. The derivative 2bx, right? The derivative 2x would be 2. The derivative 2bx is 2b, right? The b's are constant. They're just hanging out. This is going to happen when x is less than or equal to 1. Then in our other case, right, we're going to get 4ax cubed, right? The a is just a constant. It hangs out. Minus 8bx. Kind of imagine what the derivative would be without the b, like the derivative 4x squared would be 8x, and then just add the b back in, put a b in both of them. Right, and then minus 3, that's when x is greater than 1. So we're going to set those two equal to each other. 6ax plus 2b will be equal to 4ax cubed minus 8bx minus 3. And if you want to plug in 1 as you go, you can. Or if you want to do it in the next line, you can. I'm showing a lot of work. Honestly, both lines that I'm showing, you could probably even do in your head. And just jump to the third line that I'm going to write. But it's our notes, so I like to show more work than we need to. But again, if you jumped straight to this line here, you would be fine. So here's our second equation. So we have two equations, we have two variables, right? We call that two equations, two unknowns. Anytime you have two equations, two unknowns, you can always solve. 3 equations, 3 unknowns, you can solve. 4 equations, 4 unknowns, you can solve. The way we do that is we just isolate one of our variables and plug them into the other equations. So it really just depends on you. You can start with equation 1 or equation 2, doesn't matter. Just whichever one you look at and like, I want to solve for that. So I'm going to use the first equation. And I'm going to solve for a, because I see a 3a and an a that looks like I can kind of easily subtract. So I'm going to move my a's all to the left side. I'm going to move everything else to the right side. So this is going to give us 2a equals negative 6b minus 4. And then I'm going to divide everything by 2. And that gives me a equals negative 3b minus 2. So we're going to take that negative 3b minus 2, and we're going to plug it everywhere we see an a in this equation. Make sure you're plugging it in for a, right? Don't make the mistake I made in the last one. So this is going to give us 6 times negative 3b minus 2 plus 2b. If you wanted to combine like terms first, that probably would make things easier. Like if you subtracted the 4a over and added the 8b over, it might make things a little bit cleaner, but I'm doing it this way just to show that you don't have to do that. All we have to do is plug in the negative 3b minus 2, and now we can see we only have one variable. We can solve this. So if we distribute, we get negative 18b minus 12 plus 2b equals negative 12b minus 8 minus another 8b minus 3. Now we can get our like terms, but only for each side. So this is negative 18 plus 2 will give us negative 16b minus 12. On the right side, negative 12b minus 8b will be negative 20b. And negative 8 and negative 3 is negative 11. So I'm going to put all the b's to the left side, all the numbers to the right side. So I'm going to add 20b over to both sides. And we'll add 12 to both sides. So this gives us positive 4b equals positive 1. So we get b is equal to 1/4. And that is the correct answer. Now that we have our b, now we plug that in to this equation where we had isolated a. So we get a equals negative 3 times 1/4 minus 2. That's a is equal to negative 3/4 minus 2 is going to become 8/4. So we get a equals negative 3 minus 8 will give us negative 11 over 4, and that is again the right answer. So those are our two answers. Now, it would be a lot of work, but you can technically check these answers by plugging in a, b, and 1. If you plugged in a, b, and 1 to this part and this part, you should get the same answer. And if you plugged in a, b, and 1 to this part and this part, you should get the same answer. Now, it can be a little bit tricky, especially with the fractions. So just kind of trust your work. But that is how, if you had a lot of extra time on a test, that is how you could check your answer. Okay. So hope this video made sense. Again, just kind of remember that a big common question is this: what two values will make it continuous and differentiable or differentiable? And our process was to set the values equal to each other, take the derivative, set them equal, and plug in our value. And the other type of question could be, basically just that, is this differentiable case? And if we are showing our work, we have our two rules. And if we're more just looking on a graph, then we kind of just want to remember these four cases are the corners, the cusps, the vertical tangents, and then anywhere it's not continuous. So that's our summary of what we learned today.